Our solar system has a hidden frontier we have never seen. It is called the Oort Cloud, a vast and distant shell of ancient ice at the very edge of the Sun's influence. By the end of this journey, you will discover 25 unexplained phenomena that could rewrite the story of our cosmic home. What if a hidden star triggers mass extinctions from the shadows? Could alien probes be hiding in that endless freeze? We are about to become cosmic detectives, piecing together clues from the deepest dark. What do you believe is waiting for us in that unimaginable cold? Our first mystery is a shadow on the Sun's own family. For decades, a radical idea has persisted among astronomers, the suggestion that our Sun is not alone. This is the Nemesis hypothesis, the theory of a dark twin. The idea proposes a small, dim star, likely a red dwarf or a brown dwarf, sharing the Sun's orbit at an immense distance. Its gravitational home would be deep within the Oort Cloud, and its influence would be catastrophic and clockwork. Every 26 million years or so, as the theory goes, this invisible giant's orbit would carry it through the densest fields of icy debris. Its gravity would act like a cosmic cue ball, scattering countless comets from their stable paths. A rain of primordial ice would then begin a long fall sunward, a celestial storm lasting thousands of years, with some comets inevitably striking Earth. The chilling part is that this is not pure fantasy. The fossil record on our own planet shows a disturbing pattern. Studies of extinction events reveal a potential rhythm. A pulse of catastrophic die-offs approximately every 26 to 30 million years. The timing is eerily suggestive. Could a distant, unseen star be the silent conductor of life's greatest tragedies? The search for Nemesis has been exhaustive. Powerful sky surveys have mapped countless stars, searching for any hint of this dark companion. Yet, no object matching its predicted profile has been found. This absence is not a simple dismissal, however. It deepens the mystery. Perhaps Nemesis is so faint, so cold, that it hides perfectly in the infrared gloom. Maybe its orbit is far more eccentric than we guessed, taking it on a millennia-long journey we have not yet witnessed. Or perhaps the gravitational fingerprints we attribute to a star are actually caused by something else entirely, something even more strange waiting in that dark shell. For now, the invisible giant remains a ghost in the data, a hypothesis that refuses to die because it offers a terrifyingly elegant solution to one of Earth's oldest riddles. That missing star is not the only ghost pulling strings from the dark. Our own robotic explorers have felt an invisible hand. Decades ago, as the Pioneer 10 and Pioneer 11 spacecraft sailed beyond the planets, scientists tracking their trajectories noticed something deeply wrong. The probes were slowing down, not from solar wind or the faint drag of interplanetary dust, but from an unknown, constant force. It was a tiny, persistent tug back toward the Sun, a deceleration so slight it was like a feather's weight pressing against a car, yet it was undeniably there. This was the Pioneer anomaly, a gravitational mystery written in the silent language of radio signals across billions of miles. For years, this subtle drift defied all conventional explanation. Engineers checked and rechecked for gas leaks from the spacecraft thrusters, for the gentle pressure of sunlight itself, even for the heat radiating from the probe's nuclear power sources, pushing them like tiny photon engines. While some of the effect was eventually attributed to this thermal recoil, a whisper of the anomaly remained unexplained. This is where our gaze turns to the Oort Cloud. Could the answer lie not on the spacecraft, but in the space they were traveling through? Some theorists proposed that the unseen mass responsible for this tug was not behind the probes, but ahead of them. What if the Oort Cloud is far more massive than our models predict? What if it holds not just icy comets, but vast, diffuse clouds of dark matter, the mysterious substance that makes up most of the universe's mass but refuses to interact with light? Or perhaps hidden within that deep freeze are unknown planetary bodies, cold failed stars or rogue worlds, whose combined gravity creates a detectable drag at the solar system's edge. The debate continues because this is more than a puzzle about two old spacecraft. It is a potential crack in our understanding of gravity itself in the loneliest parts of our own system. The Pioneer anomaly suggests that out where the Sun is just a particularly bright star, the rules might be subtly different. It hints that the map of our solar system is incomplete, and that the blank spaces labeled Oort Cloud may contain not just frozen relics, but active, massive secrets that gently pull on everything that passes by. Gravity was not the only rule broken by a visitor from the dark. In October 2017, telescopes on Hawaii detected a faint streak of light moving at impossible speed. It was the first interstellar object ever seen passing through our solar system, and they named it Oumuamua, Hawaiian for scout. This was no ordinary comet or asteroid. Its shape alone was bizarre, estimated to be up to 10 times longer than it was wide, tumbling through space like a cosmic cigar. But the real mystery was how it moved. As it raced away from the Sun, something was pushing it. Scientists tracking its path measured a slight but undeniable acceleration that could not be explained by gravity alone. Comets often get such a boost from outgassing. When sunlight heats their icy surfaces and jets of vapor act like natural rocket engines. Yet Oumuamua showed no visible coma, the cloud of gas and dust that surrounds an active comet. No tail, no spewing debris, it was accelerating in total silence. This anomaly sparked a firestorm of speculation. Could this be a piece of alien technology? The suggestion, led by Harvard astronomer Avi Loeb, was that Oumuamua might be a light sail, a thin, reflective fragment of some ancient probe pushed by the pressure of starlight itself. But here is where our journey takes a turn back toward the Oort Cloud. What if Oumuamua did not come from a distant star at all? Its incredible speed suggested an origin far beyond our Sun, but its trajectory held a curious possibility. Some orbital calculations show it could have been moving relatively slowly for millions of years before its encounter with our Sun, a speed consistent with an object originating from the Oort Cloud itself. Imagine a scenario where an alien probe, or a piece of one, entered our solar system eons ago. It could have been captured by the Sun's gravity, settling into a slow, frozen orbit in that distant reservoir. There it would wait, a silent sentinel in the deep freeze, until a chance gravitational nudge from a passing star or a hidden planet within the cloud sent it tumbling sunward. We would see it as an interstellar visitor, but its parking place was our own backyard all along. The natural explanations remain compelling. Perhaps it was a shard of a Pluto-like world, a chunk of solid nitrogen ice from another system that outgassed in a way we simply could not detect. Yet the absence of that telltale coma lingers. Oumuamua presented us with a perfect Rorschach test in the sky. We saw either a strange new type of natural object, challenging our understanding of planetary formation, or the first tantalizing fragment of something built. It has departed forever, leaving behind only a trail of data and a profound question hanging in the silent dark. What else is drifting out there, not from between the stars, but from the frozen attic of our own solar system? That silent, drifting object was not the only messenger from the dark. On a sweltering Ohio night in August 1977, a different kind of signal arrived, one written not in trajectory but in sound. Astronomer Jerry Amon was reviewing data from the Big Ear radio telescope, a machine listening to the hiss of the cosmos. His eyes scanned a printout of alphanumeric characters representing signal strength, and there it was, a vertical column so intense it leapt off the page. He circled it in red ink and wrote a single, emphatic word beside it. Wow, that exclamation gave the signal its immortal name. For 72 seconds, a burst of radio waves 1 billion times stronger than the background noise blared from a point near the star group Chi Sagittarii. It was a narrowband transmission, precisely the kind a civilization would use to cut through the cosmic static, and then it vanished, never to be heard again. For decades, the WOW signal has stood as the strongest candidate for a potential artificial broadcast from beyond Earth. Its origin has been hunted like a ghost, with explanations ranging from a passing comet to secret military tests. Yet one compelling alignment has been largely overlooked. The direction the Big Ear telescope was pointed that night toward the constellation Sagittarius is also the general direction of our solar system's own Oort Cloud. Could the source have been unimaginably closer than a distant star? The implications are staggering. If the signal originated from within that icy shell, it forces us to confront two equally profound possibilities. The first is natural, a freak cosmic event we have never witnessed, perhaps a hyper-rare interaction between a comet and a cloud of interstellar plasma, or the explosive breakup of a massive, icy body releasing a focused burst of energy. The second possibility is the one that ignites the imagination. What if it was a beacon, not from a star hundreds of light years away, but from something or someone already here? An automated probe dormant for eons in the deep freeze, powering up for a single diagnostic pulse, a relay station left by a past visitation briefly coming online. Or even a signal meant not for us but bouncing between outposts hidden in that vast darkness. The silence that followed is just as telling. No repeat signal has ever been detected, despite countless searches aimed at that same patch of sky. This fits a chillingly logical pattern for an Oort Cloud origin. A natural event would be a 1 in a billion occurrence, unlikely to repeat. An artificial source, however, might have been a single, automated handshake that failed to get a reply, or a piece of machinery that transmitted once and then fell permanently silent, its power spent, drifting again into an eternal, frozen sleep. The WOW signal remains a perfect cosmic mystery, a one-word question mark etched into a data sheet. It tells us that on one quiet summer night, something extraordinarily powerful spoke from the void in a language we almost understood. And the quietest, most unsettling place it could have called home is the frozen frontier we are just beginning to contemplate. That unanswered signal echoes a deeper disturbance in the dark, a gravitational whisper felt not by our ears but by the paths of distant ice. Far beyond Neptune, in the realm of the extreme trans-Neptunian objects, astronomers have found a pattern that should not exist. These are small, icy worlds on immensely long orbits, taking thousands of years to circle the Sun. Individually, their paths seem random, but when you map a specific group of them, a startling clue emerges. Their orbits are clustered. They make their closest approach to the Sun, a point called perihelion, in the same general region of space, and their orbital paths are tilted in a similar direction. This is like finding a dozen scattered leaves in a vast, windy field, all somehow aligned. In the emptiness of the outer solar system, such a tight grouping is astronomically unlikely to happen by chance. Gravity is the only sculptor that could arrange them so neatly, and the only artist powerful enough for the job would be a world we have never seen. This is the hunt for Planet 9, a hypothetical giant lurking in the perpetual twilight. The mathematical predictions are breathtaking. To shepherd those distant orbits, this hidden world would need to be massive, perhaps 5 to 10 times the size of Earth. Its own orbit would be a long, stretched ellipse, swinging from a point perhaps 300 times farther from the Sun than Earth is, out to a mind-numbing 600 times that distance or more. At its most distant, its year would be 20,000 Earth years long, and the Sun would appear as little more than a piercingly bright star in an otherwise black sky. This places its realm squarely within the inner Oort Cloud, making it not just a planet but a permanent resident of that mysterious frontier. Finding it, however, is a monumental challenge. At such distances, it reflects almost no sunlight, becoming a true needle in the cosmic haystack. Our most powerful telescopes must scan enormous swaths of the darkest sky, looking for the faintest, slowest moving dot against a backdrop of fixed stars. It is a search conducted in pixels and probabilities, yet the implications of its discovery would be revolutionary. Planet 9 would not just be a new planet, it would be a new class of world, a solar system exile that holds profound influence. Its gravity could be the hand that periodically stirs the Oort Cloud, sending comets inward. It could explain other orbital oddities in the outer solar system, rewriting the story of how our planetary family formed and evolved. Most compellingly, its existence would prove that our census of the solar system is not just missing a few small rocks, but an entire giant, a ghost planet whose silent pull has been shaping the fates of distant worlds for billions of years. The search for Planet 9 is a hunt for a missing giant, but what if the force sculpting those distant orbits is not a single world, but something far more diffuse and strange? Our sixth phenomenon suggests the Oort Cloud itself may be wrapped in a ghostly shroud of the universe's greatest mystery. Astronomers call it the dark matter donut, a local halo of invisible mass. We know dark matter exists because we can see its gravitational handiwork, holding galaxies together like invisible scaffolding, yet we have never directly detected a single particle of it. The leading theory is that this mysterious substance forms vast, spherical halos around galaxies, but some models suggest it could also clump in smaller, denser streams. Our solar system, as it orbits the center of the Milky Way, might be sailing through one of these subtle rivers, and where would this dark matter naturally collect? The answer lies in the Sun's own gravitational well, particularly in the distant, quiet reaches of the Oort Cloud. Picture this not as a swarm of comets, but as a vast, diffuse ring of pure potential, a donut-shaped reservoir of particles that do not reflect, emit, or absorb light. They are there only by the weight of their gravity. This invisible mass could have profound effects. First, it would subtly alter the orbits of long-period comets in ways that pure Newtonian physics, accounting only for visible matter, cannot fully predict. The strange clustering we see might be influenced not just by a hidden planet, but by the gentle, pervasive tug of this dark matter halo. Even more intriguing is the possibility of annihilation. Some theories propose that dark matter particles are their own antimatter opposites. When two such particles collide, they would annihilate each other in a flash of energy, releasing gamma rays. If the Oort Cloud is dense with dark matter, these tiny, constant annihilations could generate a faint, uniform heat signature, a whisper of warmth in the deepest cold. Our telescopes have detected unexplained gamma-ray backgrounds from the galactic center, but a local source in our own solar system's attic would be a staggering discovery. It would mean we are not just surrounded by dark matter, we are living inside a local concentration of it. The implications rewrite our place in the cosmos. This donut would be a natural laboratory, offering a chance to study the universe's dominant substance right here at home. It could also solve another puzzle, the missing mass problem within our own solar system. The combined gravity of all our known planets and comets does not quite account for all the gravitational effects we observe at the very edges. A dark matter halo woven through the Oort Cloud could be that missing piece, the invisible glue that has been subtly guiding the dance of ice in the dark for eons. We are left with a haunting vision, not of a single hidden world, but of an entire frontier permeated by an unseen, interactive presence, a ghostly architecture whose silent physics may be the true ruler of the outer dark. The ghostly pull of dark matter is a silent force, but its effects could be written in the most violent chapters of Earth's own history. Deep in the rock layers beneath our feet, there is a record of catastrophe, a rhythm of destruction that points a finger directly at the Oort Cloud. This is the comet shower mystery, the evidence that our planet is periodically bombarded by swarms of icy visitors from the deep freeze. Paleontologists studying the fossil record have long noted a disturbing pattern. Major extinction events like the one that wiped out the dinosaurs do not seem to be random tragedies. Statistical analyses suggest a pulse, a beat of devastation recurring roughly every 26 to 30 million years. It is as if a cosmic clock is ticking, and when it strikes, life on Earth pays the price. But fossils are only one part of the story. Geologists have found corresponding evidence in impact craters. When the ages of large, known craters are plotted on a timeline, they too appear to cluster in waves, aligning eerily with the proposed extinction cycle. This is not the work of a single, stray asteroid from the asteroid belt. This pattern suggests a storm, a sudden influx of multiple impactors over a relatively short geological window. The source of such a storm could only be one place: the Oort Cloud. Imagine that distant shell as a vast, frozen arsenal, holding trillions of cometary nuclei in unstable orbits. For most of history, they drift in a deep gravitational sleep, but every 26 million years or so, something must pass through and stir the nest. The gravitational wake of a passing star, the rhythmic tug of our solar system bobbing through the dense plane of the Milky Way galaxy, or the hypothetical orbit of a hidden perturbed-like nemesis, any of these could act as a trigger. Like a stone thrown into a pond of sleeping ducks, the disturbance sends ripples through the cloud, dislodging countless chunks of primordial ice. They begin a long, slow fall sunward, a migration that takes thousands of years. As this scattered swarm converges on the inner solar system, the odds of a collision with Earth skyrocket. We would not be hit by just one comet, but by many over centuries. The consequences are apocalyptic. A single large impact can blot out the sun with dust, trigger global firestorms, and collapse ecosystems. A shower of them would be a cascading nightmare, a series of climatic punches from which life would struggle to recover. The search for the precise trigger is one of astronomy's great detective stories. Is it a stellar sibling on a monstrous orbit, as the nemesis theory proposes? Is it the solar system's vertical motion through the galactic disk, where tidal forces might strip comets loose? Or is it the combined influence of that hypothetical dark matter halo or the unseen planet 9? Each possibility paints a different picture of our cosmic neighborhood, but they all lead back to the same conclusion. The Oort Cloud is not a static museum. It is a loaded gun, and something out there appears to be pulling the trigger on a schedule written in stone and bone. The clock is always ticking, and the next shower may already be falling inward, a silent rain of ice beginning its multi-million-year journey toward an unsuspecting world. A cosmic civilization advanced enough to build a Dyson sphere would face an ultimate dilemma. Their star's energy is finite, and the waste heat from their civilization would eventually make their home system glow like a beacon in the infrared, visible to any watching eyes across the galaxy. For a species concerned with privacy or survival, the solution is simple. You move your entire operation to the darkest place you can find. You build your megastructure not around a bright, young sun, but around a failed one, a cold brown dwarf or a dim red star adrift in the interstellar void. And where is the perfect hiding place for such a project? The answer is the Oort Cloud. Within that vast, unlit shell, our own solar system may already host the perfect real estate for an alien engineering project on a staggering scale. A brown dwarf, an object too massive to be a planet but too small to ignite as a true star, would be a cold, dark ember. To our optical telescopes, it is essentially invisible. Yet to a super-advanced civilization, its faint, residual heat and gravitational potential could be a valuable resource. Encase it in a swarm of orbiting energy collectors, a Dyson swarm, and you have a power plant running for trillions of years, hidden in plain sight at the very edge of a star system. Detecting such a structure with our current technology borders on the impossible. We would not see a solid shell, a concept that is mechanically improbable. Instead, we might detect a statistical anomaly, As this megaswarm orbits its dark host, it would occasionally, randomly, pass in front of distant background stars. From our vantage point, we would see those stars momentarily wink out, not with the clean dip of a planet's transit, but with a strange, irregular pattern as countless orbiting panels and habitats block the light in a complex, shifting mosaic. More promising is the infrared signature. Even a Dyson swarm collecting energy must radiate waste heat. A brown dwarf with a temperature of just a few hundred degrees would have a specific infrared glow. A swarm around it would alter that signature, making it look oddly uniform or producing excess heat at wavelengths that do not match any known natural object. Our sky surveys like WISE have catalogued millions of infrared sources looking for just such anomalies. The search has turned up puzzling objects like the famous Boyajian star with its bizarre, irregular dimming, though that lies far beyond our solar system. The profound question for the Oort Cloud is this: what if we found an infrared anomaly that is not light years away, but is moving with us, a faint, warm speck sharing our sun's journey through the galaxy? It would be the ultimate cosmic hide and seek. We would be faced with evidence that we are not the sole tenants of our solar system, that a presence of unimaginable age and sophistication has been quietly residing in our farthest attic, harvesting the dim glow of a failed sun, utterly indifferent to the tiny, warm world orbiting the bright star next door. The profound quiet of that frontier may be the perfect canvas upon which the universe paints its smallest, strangest secrets. Our ninth phenomenon takes us from the scale of hidden worlds to the very fabric of reality itself. At the unimaginable edge of the solar system, in the near-perfect vacuum and microgravity of the Oort Cloud, space might not be empty at all. It could be fizzing. Quantum mechanics tells us that what we perceive as empty space is a seething sea of potential. At the tiniest scales, pairs of virtual particles and antiparticles constantly wink into existence, borrowing energy from the vacuum before annihilating each other almost instantly. This is the quantum foam, the turbulent foundation of spacetime. On Earth, or even near the planets, this effect is drowned out. Gravity is strong, electromagnetic fields are everywhere, and the sheer density of matter and energy masks these fleeting fluctuations. It is like trying to hear a single raindrop in the middle of a hurricane, but the Oort Cloud is different. It is the quietest place for light years in any direction. The sun's gravity is a faint whisper, light is a distant memory, and the background noise of the cosmos is reduced to a faint hiss. Here, in this profound isolation, some physicists speculate that the quantum foam might become detectable. The fluctuations in spacetime itself could be large enough or persistent enough for our instruments to finally sense. Imagine a future probe, a silent sentinel parked in that deep dark, equipped not with cameras for comets, but with lasers of unimaginable precision. It might fire a beam of light to a mirror a few meters away and measure the time it takes to return. In our world, that time is constant, but in a region where quantum foam is active, spacetime itself is churning at the smallest scale. The distance between the laser and the mirror would not be fixed. It would be jittering, fluctuating by distances far smaller than an atom, as the very fabric of the path roiled with temporary virtual particles and tiny, nascent wormholes. The laser's return time would show a subtle, statistical noise, a signature of the universe's underlying graininess. Another method could involve supercooled gyroscopes spinning in perfect frictionless isolation. In smooth spacetime, their axis of rotation would remain fixed, but spinning within a quantum foam, that axis might exhibit a tiny, unpredictable drift, pushed by the fleeting gravitational effects of virtual mass popping in and out of existence. Detecting this would be a monumental achievement, a direct window into a realm where gravity and quantum mechanics are supposed to merge, a place our current laws of physics cannot fully describe. The Oort Cloud, therefore, transforms from a mere reservoir of ancient ice into the ultimate physics laboratory. Its value is not in what fills it, but in what it lacks: noise, interference, and strong gravity. It offers a pristine environment to ask the universe its most fundamental questions. If we could park an experiment there and listen to the hum of empty space, we might finally hear the true voice of the vacuum, a sound that has been echoing since the beginning of time, waiting in the deepest cold for someone quiet enough to listen. The profound quiet of the quantum foam is a testament to the Oort Cloud's age, a silent witness to events that reshaped our solar system before the Earth even formed. Our solar system's early days were a chaotic ballet of giant worlds, and we may have lost one of the principal dancers. This is the ancient relic hypothesis, the compelling idea that a fifth giant planet once orbited our Sun, only to be violently exiled to the frozen dark. The story begins with the Grand Tack model, a leading theory of planetary migration. It suggests that in the first 100 million years after the Sun ignited, Jupiter and Saturn performed a gravitational dance, moving inward toward the Sun before reversing course and migrating back out. This cosmic shuffle would have scattered the primordial disk of gas and debris, violently disrupting the orbits of the other young giants, Uranus and Neptune. Computer simulations consistently show that to achieve the planetary arrangement we see today, a fifth ice giant, similar in size to Uranus or Neptune, likely existed. Its fate was not to find a stable orbit. The gravitational turmoil, a gravitational pinball game between the massive worlds, would have slingshotted this unnamed giant out of the inner system entirely. Flung toward the stars, it instead became captured by the Sun's weak gravity at the very edge of its influence, settling into a distant, lonely orbit within what would become the Oort Cloud. The question is, what became of it? One possibility is that the planet itself is still out there, a frozen, dormant titan. At those distances, the Sun is a mere pinprick of light. Any atmosphere it once had of hydrogen and helium would have long since frozen into exotic ices, coating a rocky or watery core in a perpetual glacier 1,000 miles thick. It would be a dead world, but a perfectly preserved one, a time capsule holding the chemical secrets of the solar system's birth, uncontaminated by 4.5 billion years of solar heat and cosmic rays. Finding it would be the archaeological discovery of the ages, a Rosetta Stone written in ammonia ice and ancient rock. The other, perhaps more likely, scenario is that the planet did not survive the ejection intact. The gravitational forces involved could have been so extreme that they tore the world apart. In this case, the Oort Cloud is not hiding a whole planet but its graveyard. Trillions of fragments, from mountain-sized chunks of icy mantle to pebbles of primordial core material, would have been scattered across that distant shell. These would not be typical comets, which are thought to be fluffy aggregates of ice and dust. These relics would be denser, richer in minerals and heavy elements, the shattered remains of a fully formed world. A comet originating from such a fragment would have a completely different chemical signature when it finally visits the inner solar system, one that would leave astronomers utterly baffled. This hypothesis transforms our view of the Oort Cloud from a simple comet factory into a cosmic museum of lost history. Every icy body we detect from that region could be a piece of a deeper puzzle. Is that strange, dark object a remnant of a lost giant's core? Does the unusual ratio of gases in that comet's tail match what we'd expect from a shattered Uranus? Each new visitor from the deep holds the potential to be a clue, a piece of debris from a catastrophic event that helped carve the solar system we call home. The ghost of the fifth giant may not pull on orbits today, but its legacy could be frozen into the very fabric of the cloud, waiting for us to recognize the fragments of a world that never was. That shattered world's debris field offers more than just ancient rubble. It provides the perfect raw materials for a patient, unseen observer. The concept of a Bracewell probe is a chillingly logical answer to a cosmic question. If an advanced civilization wanted to study a star system like ours, why announce your presence with powerful radio signals? Instead, you send a fleet of autonomous, self-repairing scouts. These are not massive ships with living crews. They are sophisticated machines, perhaps no larger than a truck, designed to enter a target system and find a place to hide. Their mission is simple: observe, collect data, and wait. And there is no better hiding place in our entire solar system than the Oort Cloud. Think about the advantages from an alien engineer's perspective. The cloud is unimaginably vast, offering countless places to conceal a small, dark object among trillions of others. The resources are already there. A smart probe could harvest water ice for reaction mass, use rare metals from asteroid or planetary fragments for repairs, and power itself for millennia with a tiny nuclear reactor or advanced solar panels, gathering the faintest trickle of sunlight. Most importantly, it is far from the noise. From that distance, our entire inner solar system is laid out like a map. The probe could watch the slow dance of our planets, monitor our radio and television leakage as it expanded outward at the speed of light, and study our technological growth without ever risking detection. It would have a front-row seat to the entire history of human civilization, seeing our first radio broadcasts from the early 20th century only now reaching its location. But the most profound idea is that these sentinels would not be alone. A monitoring network would not rely on a single point of failure. There could be dozens, hundreds, even thousands of them scattered throughout the cloud, forming a silent web. They could communicate with each other using tight beam lasers or quantum entanglement, passing information from probe to probe, creating a distributed intelligence spanning billions of miles. This internal network would be completely invisible to us, as its signals would never be aimed at Earth. It would be a conversation happening in our attic, in whispers we are not meant to hear. The purpose of such a network shifts the paradigm entirely. This is not about making contact. It is about gathering a long-term, unbiased dataset on a developing biosphere and its accompanying technology. Are we a peaceful species? Do we show signs of becoming a spacefaring civilization, or are we trending toward self-destruction? The probes would note everything from our nuclear tests to our climate changes, from our first satellites to our potential voyages to Mars. They are the ultimate surveillance system, operating on a timescale of millennia, patiently waiting for us to either pass a cosmic test or fail it utterly. The evidence for their existence, of course, is the perfect lack of evidence. A well-designed Bracewell probe would be engineered to be undetectable by a civilization at our current level. It might only reveal itself if we stumbled upon it physically, or if it decided, according to some ancient programming, that the time for observation was over. This transforms every strange, dark object we detect on the edge of our system into a potential candidate. Is that just a dormant comet, or is it something with a purpose, watching the tiny, bright dot of Earth as it spins in the distant warmth? The silence from the Oort Cloud may not be emptiness at all. It could be the quiet, focused attention of guests who arrived long before we learned to look up. Our solar system's attic may hold more than just our own discarded history. It could be a museum for the entire galactic neighborhood. The vast gravitational net of our sun does not just trap objects born here, it can also capture wanderers from other stars. In the dense stellar nurseries where suns are born in clusters, young stars pass close to one another, their gravity playing a game of cosmic catch with the icy debris surrounding them. A comet orbiting one star can be tugged free, sent drifting into the interstellar void. If such a wanderer later passes near our sun, especially in the diffuse, loosely bound region of the Oort Cloud, it can be captured. This process transforms our distant shell into a collection agency for interstellar orphans, a frozen archive of chemistry from across the galaxy. These captured comets would be utterly unique time capsules. Unlike comets formed in our own solar system, which share a common origin in the Sun's protoplanetary disk, an interstellar immigrant would bear the distinct chemical fingerprint of its parent star. The ratios of isotopes, the varieties of organic molecules frozen within its ice, even the crystalline structure of its water, all of it would be a message written in atoms declaring its foreign origin. Finding and studying one would be like receiving a perfectly preserved sample from another stellar nursery, a physical piece of a place we may never directly visit. The hunt for these primordial immigrants is already underway, but it is a search for a needle in a haystack of needles. Astronomers scrutinize the orbits of every new long-period comet discovered. A true interstellar capture would have an orbit that is not just extremely long, but hyperbolic, meaning it is permanently bound to the Sun, but on a path that clearly suggests it was not born here. Its velocity when first spotted would be a crucial clue, hinting at an origin beyond the Sun's gravitational influence. We may have already found one candidate, Comet Matchholes 1. This strange visitor has an orbit and a chemical composition that is profoundly odd, with extremely low levels of certain carbon-nitrogen molecules common in other comets. Some researchers suggest it could be an interstellar interloper captured long ago, its unique chemistry a relic of a different cosmic forge. Proving this definitively, however, requires a close-up visit. Imagine a future mission designed not to chase objects leaving our system like Oumuamua, but to journey into the Oort Cloud itself, to rendezvous with a dormant comet and drill into its ancient ice. The data returned would be revolutionary. By comparing its deuterium to hydrogen ratio, a fundamental signature set during stellar birth, we could potentially identify what type of star it came from. Finding complex organic molecules unknown in our own solar system would suggest the building blocks of life are not just common but universal, assembled in different ways around different suns. Each such comet is more than a scientific specimen. It is a bottled message from a distant past telling us that the ingredients of worlds are shared, traded, and scattered across the light years, and that our own quiet corner of the galaxy is a crossroads for these frozen travelers. The captured interstellar comets are messages in a bottle, but to read the fine print on a galactic scale, you would need a telescope of impossible power. Our Sun offers exactly that. Its immense mass warps the space around it, acting as a natural lens. This is not a metaphor. According to Einstein's theory of general relativity, a massive object bends passing light rays. If a distant star, galaxy, or any object lines up precisely behind our Sun from an observer's viewpoint, the Sun's gravity can focus that light, magnifying it billions of times. This sweet spot, the solar gravitational focus, is not located in the Oort Cloud but far beyond it. It forms a continuous line stretching outward from the Sun, starting at about 550 times the distance from the Earth to the Sun. For an observer or a probe positioned anywhere along that line, the Sun becomes the ultimate telescope, capable of seeing surface details on planets orbiting other stars. The image would be staggeringly clear, free from the distortion that plagues even our best space telescopes. You could map continents on an exoplanet, see cloud patterns, even potentially detect signs of cities or megastructures. It is a gift of physics, a perfect vantage point built into the fabric of our star system. Now consider a civilization that understood this principle a million years ago. Where would they place their most important observatories? The answer is obvious. They would station silent, autonomous relay stations along that gravitational focus line, each one dedicated to studying a different patch of the galactic sky. These would not be simple telescopes. They would be complex facilities, harnessing the focused light of the Sun to gather data with unparalleled resolution, then beaming that information back to their homeworld via tight laser links or storing it for periodic collection. The infrastructure for such a network would be minimal and hidden. A station could be a simple scaffold holding a collector, a transmitter, and a power source, perhaps a compact nuclear reactor or vast, thin solar panels facing the distant, shrunken Sun. From our perspective in the inner solar system, these stations would be nearly impossible to see. They are tiny, dark, and lost in the glare of the sun if we look toward them, or impossibly faint if we look from the side. But we might detect their side effects. Any advanced machinery generates waste heat. Even with perfect efficiency, the process of collecting, processing, and transmitting vast amounts of data would produce a thermal signature. Our most sensitive infrared telescopes, like the upcoming Nancy Grace Roman Space Telescope, could scan the regions along the gravitational focus line, searching for anomalous point sources of heat that do not match any known natural object, like a dim brown dwarf or a rogue planet. Another signature could be in the light itself. If a relay station is actively transmitting its gathered data, it might use a powerful laser. A momentary, coherent flash from that profound darkness, especially if it repeats on a logical schedule, would be a beacon of artificiality. We would also look for shadows. If a station passed in front of a distant background star, it would cause a unique, non-repeating dip in that star's light. A brief, sharp occlusion unlike the smooth curve of a planetary transit. Projects like the Vera C. Rubin Observatory, which will scan the entire sky repeatedly, could catch such fleeting events. The profound implication is that our solar system might already be instrumented for a purpose we cannot fathom. The gravitational focus network turns our sun into a galactic eyepiece. If someone else is using it, they are not watching us. Their gaze is fixed on the deep galaxy, their sensors peering into the heart of distant nebulae and the orbits of alien worlds. We would be mere neighbors in the cosmic suburb, unaware that the most powerful telescope imaginable is operating from our own backyard, its silent data stream flowing past us toward an unknown destination. The perfect alignment for observation points away from Earth, making us irrelevant to its primary mission. We are living next to a piece of interstellar infrastructure, a library node in a network that spans the stars, and we have only just begun to look for its card catalog. The silent data streams of a hidden network would require immense power, and the signatures of that power might already be raining down on us. High above Earth, specialized detectors have been tracing the paths of cosmic rays, atomic nuclei hurtling through space at nearly the speed of light. For over a decade, one observatory in particular has recorded a baffling anomaly. It is called the Cosmic Ray Hotspot, a region of the sky roughly the size of 20 full moons where these ultra-high energy particles seem to originate. These are not just any particles, they are the most energetic phenomena in the universe, packing the punch of a professionally thrown baseball into a single subatomic speck. Their source has been a profound mystery, as their paths are bent by magnetic fields obscuring their origin. Yet this hotspot persists, a statistical excess pointing like a faint, broken compass. The leading theories point to cataclysmic events far beyond our galaxy, like active galactic nuclei. But there is a quieter, closer possibility that challenges everything. What if the source is not billions of light years away, but within our own solar system's frozen border? The Oort Cloud could be hiding the engine for this particle accelerator. One candidate is a primordial micro-black hole, a relic from the Big Bang itself. Theorized to be as small as an asteroid but with the mass of a mountain, such an object could have been captured by the sun's gravity eons ago. If it is slowly evaporating through Hawking radiation, its final moments would be a violent burst of energy, a flash of high-energy particles and gamma rays. A micro-black hole in its death throes, hidden in that vast dark, could be the pinpoint source of the hotspot. Another possibility is the remnant of a neutron star merger. The collision of these ultra-dense stellar corpses is known to forge heavy elements and release torrents of radiation. A fragment of such an event, a shard of exotic matter or a powerful magnetic knot, could have been flung into interstellar space and later captured by our Oort Cloud. This cosmic cinder, still pulsating with ferocious energy, would act as a natural particle accelerator, its intense magnetic fields whipping charged particles to near light speed. A third, equally plausible source is not an object but an event frozen in time. An ancient supernova shock wave, a wall of energized plasma from a star that died before our sun was born, could have plowed into the Oort Cloud. As this wave of force interacts with the trillions of icy bodies, it could generate shock fronts and magnetic turbulence, a natural laboratory that continuously accelerates particles to extreme energies. The cloud itself would become a luminous fog in high-energy particles, with the hotspot marking the direction of the most intense interaction. The implications are staggering. If the source is local, it means one of the most energetic puzzles in astrophysics is not a distant quasar, but a neighbor. It transforms the Oort Cloud from a passive freezer into an active physics engine, a place where the universe's most violent processes are either trapped or ongoing. Detecting the corresponding gamma rays or neutrinos from that specific direction could be the key. A future neutrino telescope, or more precise cosmic ray observatories, might one day trace these particles back to a single, faint object or diffuse, glowing region in the absolute dark. We would then have to explain not just what it is, but how it got there. Is it a captive piece of a galactic catastrophe or a ticking relic from the dawn of time? The answer is written in particles that strike our atmosphere with the force of mysteries we are only beginning to measure. The cosmic particle accelerator is a relic of ancient violence, but the Oort Cloud may also hold the lost children of our own planetary family. The ice giants Uranus and Neptune are strange, tilted worlds with thin rings and modest collections of moons, yet their current families might be only the survivors of a much larger brood. During the solar system's chaotic youth, as these giants migrated outward, their gravitational influence was a storm of unimaginable force. Large moons forming in orbit around them would have faced a brutal fate. The shifting gravity of the passing giants, particularly Jupiter and Saturn, could have plucked these nascent satellites right from their orbits. Instead of crashing into their parent planet or being flung into the sun, many of these lost moons would have been given just enough energy to escape, but not enough to leave the sun's grip entirely. Their new home became the distant, frozen realm of the Oort Cloud. There, these phantom moons wander not as moons anymore, but as independent dwarf planets or the largest cometary nuclei imaginable. They are worlds in their own right, some potentially hundreds of miles across, with their own geology and chemistry frozen in time. Their surfaces are archives of a different sort. Shielded from the sun's warmth for billions of years, they have never experienced the thawing and refreezing that alters comets visiting the inner solar system. This means any organic compounds that formed on or within them, the carbon-rich building blocks of life, remain in a state of perfect preservation. Think of a complex molecule, a chain of carbon atoms forged in the chemical laboratory of a moon's subsurface ocean or within its icy crust. Near a planet, radiation and heat would break it down over eons. In the Oort Cloud, that molecule is essentially in deep storage at near absolute zero, unchanged since the day it formed. Finding one of these lost moons would be like opening a freezer that has been sealed since the solar system's infancy. We could sample probiotic chemistry in its most primordial state, seeing the exact ingredients that were available before life emerged anywhere. Their surfaces might hold a record of impacts from that violent era, craters upon craters telling the story of the early outer solar system. Some could even be captured interstellar objects themselves, making them double relics. The search for them is a monumental challenge as they reflect almost no light, but their gravitational signature might one day give them away. Each is a silent testament to a family broken apart, a world that once circled a blue giant in the twilight, now alone in the endless dark, carrying within its frozen heart the untouched recipe for life itself. The frozen chemistry of lost moons hints at a universe pregnant with potential, but what if that potential was not random but delivered? This brings us to the biotic delivery system, the radical idea that life itself can hitch a ride on comets. It is called panspermia, the hypothesis that microorganisms or their building blocks are not confined to a single world, but can be transported across the vast interstellar distances, shielded within the icy hearts of comets and asteroids. When such a cosmic traveler strikes a young, habitable planet, it could inoculate that world with the seeds of biology. The Oort Cloud, holding trillions of these icy vessels, becomes the ultimate reservoir for this process, a galactic library of life's potential blueprints. The logic is compelling. We know that hardy microbes like tardigrades can survive the vacuum of space and extreme radiation. We know that comets contain water and complex organic molecules. And we know that impacts happen. A life-bearing comet from another star system could be captured by our sun's gravity into the Oort Cloud, waiting for a gravitational nudge to send it on a collision course with early Earth. Our entire biosphere could, in theory, be the result of a successful delivery from that distant deep freeze. But there is a more intentional version of this story, one that transforms the cloud from a random archive into a deliberate garden. This is directed panspermia. Imagine a civilization, perhaps one that arose on Earth billions of years before us and has long since vanished, or one from a distant star facing an existential crisis. Their sun is dying, or a cosmic catastrophe is inevitable. To preserve their biological legacy, they undertake a project of staggering patience. They genetically engineer incredibly resilient microbes, or perhaps encode their own genetic information into durable molecular structures. Then they load these biological packages onto thousands of robotic probes. The mission is not to explore, but to seed. These probes voyage to neighboring star systems, and finding stable Oort Cloud-like structures, they disperse their cargo. They inject these capsules of life into the icy bodies there, knowing that over millions or billions of years, gravitational interactions will slowly scatter some of those seeded comets into the inner systems, where they might crash into planets with liquid water. Life is not just spreading, it is being strategically planted. Our own Oort Cloud could be one such garden. The microbial ancestors of all life on Earth might not have arisen in a warm little pond here, but in a lab on a world we will never know, packaged and shipped to our solar system's outer shelf for safekeeping and timed release. The evidence for this would be subtle, but not impossible to find. If we could retrieve a pristine Oort Cloud comet and discover within it microorganisms with a biochemistry radically different from Earth's, or with DNA that uses a different genetic alphabet, it would be a strong indicator of an external origin. Even more telling would be finding a pattern, a signature of engineering, like a microbe optimized for long-term cryogenic survival in ways no natural selection on Earth could explain, or a genetic code that contains a non-functional repeating sequence, a deliberate maker's mark left in the very blueprint of life. This idea reframes our existence in a profound way. We are not an accident of a lonely planet. We could be part of a harvest, the intended result of a project that began before our planet cooled. Our story written not just in our genes, but in the deliberate trajectory of a comet placed in the dark, waiting for its moment to fall and awaken a world. A strange harmony plays in the deepest silence of our solar system. Far beyond the orderly orbits of the planets, in the chaotic realm of the scattered disk and inner Oort Cloud, astronomers are detecting a faint, repeating rhythm. Some of these distant, icy objects, each on a lonely journey lasting thousands of years, appear to be moving in sync with the distant giant Neptune, or perhaps with the unseen hand of Planet 9. This synchronization is called an orbital resonance, a gravitational dance where the orbital periods of two bodies form a simple ratio like 2 and 1 or 3 and 2. It is the music of the spheres, but played at the edge of hearing in the coldest, darkest concert hall imaginable. Finding such a precise pattern at these staggering distances is like discovering that a handful of leaves scattered by a hurricane across a continent have all landed pointing in the same direction. It should not happen by chance. Gravity is the conductor, and for these objects to be in resonance, something must have carefully arranged them. the most straightforward explanation points to Neptune. As the ice giant migrated outward in the solar system's youth, its gravity could have shepherded some objects into these resonant orbits, locking them into a stable pattern even as they were flung to the far reaches. But the puzzle deepens with objects so distant that Neptune's direct influence is incredibly weak. Their synchronization suggests the involvement of a more distant, more massive perturber, a hidden conductor keeping time from the shadows. This is where Planet 9 re-enters the story. If it exists, its immense orbit could create a sweeping gravitational influence that organizes these distant bodies into resonant families, much like Neptune shepherds the closer Kuiper belt objects. The mathematics show that a large planet on a tilted, elongated orbit could easily produce the strange clustering and resonant patterns we see. But there is another, more subtle possibility. What if the resonance is not with a single planet, but with the combined gravitational heartbeat of the giant planets? As Jupiter, Saturn, Uranus, and Neptune orbit, their combined gravitational pull creates a complex, repeating pattern of tugs on the outer solar system. Over billions of years, this background rhythm could have gently sorted the most distant objects, nudging some into stable resonant pockets while ejecting others entirely. Mapping this distant music is a task of extraordinary patience. Each newly discovered extreme trans-Neptunian object adds a single note to the score. Astronomers must track its path for years to calculate its orbit with enough precision to hear if it is in tune with the hidden symphony. Every confirmed resonance is a clue, a data point that helps constrain the mass orbit and even the existence of the unseen conductor. This harmonic resonance does more than hint at hidden planets. It reveals that the Oort Cloud is not a static junkyard. It is a dynamic, structured environment, its history written in the slow, gravitational poetry of orbits. These synchronized objects are fossils of a violent past, frozen in arrangements that tell the story of planetary migrations and close encounters from eons ago. They are proof that the solar system's evolution did not end at Neptune's orbit, but echoed out into the vast dark, arranging the furniture in our farthest attic in ways we are only just beginning to understand. The distant music of orbital resonance hints at worlds shaped by hidden forces, and one such world has already whispered its name. Sedna is a lonely wanderer, a reddish dwarf planet locked in a dance of extreme isolation. Its orbit is a staggering ellipse that takes roughly 11,000 years to complete, carrying it from a point just beyond the orbit of Neptune out to a mind-bending distance over 900 times farther from the Sun than Earth. For most of that immense journey, Sedna resides in the inner Oort Cloud, a frozen sentinel in perpetual twilight. This strange, small world presents a tantalizing possibility that even in that profound, cold, geological hearts might still beat. The phenomenon is cryovolcanism, ice volcanoes. Unlike the fiery, molten rock eruptions of Earth, a cryovolcano on a world like Sedna would erupt a frigid slurry of water ice mixed with ammonia, methane, or nitrogen. These substances behave like lava in the deep cold, flowing slowly across a landscape where the temperature never rises above -400 degrees Fahrenheit. The very idea seems contradictory. How could a small, distant object so far from the sun's warmth retain enough internal heat to power any kind of eruption? The answer lies in two quiet, persistent engines. The first is radioactive decay. Deep within Sedna's rocky core, elements like uranium and thorium are slowly breaking down, releasing a faint, steady trickle of heat as they do. Over billions of years, this heat can build up, especially if the world is insulated by a thick mantle of ice. That heat needs an escape valve. Pressure builds until the overlying ice crust fractures, and a plume of warm, slushy ice bursts forth, refreezing into strange, glacial formations on the surface. The second engine is tidal heating. Sedna's orbit, while lonely, is not perfectly smooth. The gravitational tug of the Sun, even at its immense distance, combined with the possible influence of other unseen bodies, could squeeze and flex the dwarf planet's interior. This constant kneading, like repeatedly bending a piece of metal until it grows hot, generates internal friction and warmth. Even a tiny amount of such heating, trapped under an icy shell, could be enough to maintain a subsurface ocean of liquid water, ammonia or methane, with cryovolcanoes acting as vents to that hidden sea. Evidence for this activity would be written on Sedna's surface. Telescopic observations have already revealed it is one of the reddest objects in the solar system, a hue that could be caused by complex organic compounds called tholins. These molecules are created when simple ices like methane are irradiated by cosmic rays over eons. But what if that reddish sludge is not just a passive coating? What if it is being renewed from below, oozing out in cryovolcanic flows that constantly repaint the landscape? We might also look for signs of recent resurfacing, areas suspiciously smooth and free of the ancient craters that should pockmark such an old world, or odd, dome-like structures that resemble volcanic calderas made of ice. The implications of an active Sedna are profound. It would mean that geological life is not confined to the warm, rocky inner planets or the ice moons of the giant planets. It can persist in the deepest freeze in the smallest of worlds, sustained by the slow burn of atoms or the gentle flex of a distant tide. This transforms our view of the Oort Cloud from a graveyard of static ice balls into a realm of potential astrobiological refuges. If Sedna has a subsurface ocean warmed by radioactivity or tides, that dark, salty water could be a haven for exotic microbial life, completely independent of sunlight, thriving on chemical energy from the rock below. Each cryovolcano would then be not just a geological feature, but a potential chimney from a hidden biosphere, a sign that life's tenacity extends to the very edge of our sun's influence. Sedna becomes a test case, a single data point screaming that cold does not mean dead. It whispers that in the silent, endless dark, there may still be warmth, movement, and perhaps against all odds, a pulse. Sedna's hidden warmth suggests a dynamic history, but that history might be written in the very water that could flow beneath its ice. Water, however, is not a single substance. Its fingerprint can tell us where it was born, and that fingerprint is creating a cosmic identity crisis. The puzzle centers on deuterium, a heavy isotope of hydrogen. In every drop of water, a tiny fraction of the hydrogen atoms carries an extra neutron, making it deuterium. The ratio of deuterium to normal hydrogen acts as a chemical birth certificate, set by the temperature and conditions where the water ice first formed billions of years ago. For decades, astronomers assumed comets from the Oort Cloud, being pristine relics from the solar system's birth, would deliver water with a deuterium ratio matching Earth's oceans. The logic was beautiful and simple. If Earth's water came from comets, their water should be identical. The reality, as our probes have revealed, is a chaotic mess. When the European Space Agency's Rosetta mission studied comet 67P, it found water with a deuterium ratio 3 times higher than Earth's. Other comets have shown different values, some higher, some lower. This variation is not a minor discrepancy, it is a fundamental challenge. It means the Oort Cloud cannot be a uniform reservoir of identical ice balls. Instead, it must be a chaotic mix of distinct populations, each with its own unique origin story. One compelling explanation is that these comets formed in vastly different neighborhoods of the protoplanetary disk, the swirling cloud of gas and dust that birthed our planets. Picture the young solar system as a giant, heated platter, close to the hot, young sun, where deuterium-rich chemistry might have been favored. Icy grains could have formed before being violently flung outward by gravitational chaos. Farther out, in the colder realms of the giant planets, water with a different deuterium signature would have condensed. The Oort Cloud, acting as the solar system's attic, collected this jumbled furniture from every room. But the mystery deepens further. Some of these isotopic signatures may not be from our Sun at all. The wild outliers, the comets with ratios that are completely off the charts, could be interstellar immigrants captured from other star systems, as we discussed earlier. Their water carries the signature of a different stellar nursery entirely. This transforms the Oort Cloud from a simple solar system archive into a galactic mixing bowl. Each comet becomes a puzzle piece, but from many different puzzles. The consequence for our own story is profound. If comets have such wildly different water, then which ones, if any, delivered Earth's oceans? The answer may be that no single population did. Our planet's water could be a cocktail, a blend from many different sources, asteroids from the inner system with one ratio, comets from the inner Oort Cloud with another, and perhaps even local chemistry on early Earth contributing its own signature. The missing deuterium is not really missing, it is telling us a more complex and fascinating story. It reveals that the journey of a water molecule is a grand epic, possibly spanning light years and multiple stars before finding its way into a cloud, a comet, and finally, a glass. The Oort Cloud holds every chapter of that epic in frozen suspension, waiting for us to learn how to read them all. That cosmic fingerprint of water tells a story of journeys, but the greatest journey of all is the one our entire solar system is taking. We are not sitting still. Our Sun, with all its planets and that distant Oort Cloud in tow, is orbiting the center of the Milky Way galaxy. This grand voyage subjects our entire system to a force we rarely consider, the gentle, persistent pull of the galaxy itself. This is the galactic tide, a gravitational whisper from hundreds of billions of stars. Out in the Oort Cloud, where the Sun's grip is at its most fragile, this tide becomes a sculptor. Think of it like the ocean's tide on Earth, but on a scale so vast it defies comprehension. The Moon's gravity pulls on our planet's oceans, creating a bulge of water. In a similar way, the combined mass of the Milky Way's disk, its central bulge, and its dark matter halo tugs on the sparse material at the solar system's edge. This tidal force is not strong enough to rip comets away instantly. Instead, it is a slow, patient hand, a constant background nudge over millions of years. It works by stretching the cloud ever so slightly along the direction toward the galactic center and compressing it from the sides. For a comet in a loosely bound, unstable orbit, this steady pressure can be the final straw. The galactic tide adds just enough energy to tip the balance, plucking the comet from its tenuous hold and sending it on a new trajectory, either inward toward the Sun or outward into interstellar space. This process provides a beautiful, elegant explanation for the steady trickle of long-period comets we observe. Not every comet needs a passing star or a hidden planet to dislodge it. The Milky Way itself, simply by being there, acts as a cosmic gardener, slowly shaking the outer branches of our solar system so that a few frozen fruits fall inward every year. Modeling this effect, however, is a nightmare of complexity. Astronomers must account for the Sun's motion through a galaxy that is not a smooth soup of mass, but a structured, clumpy spiral with arms, star clusters, and giant molecular clouds. The tidal force is not constant. It fluctuates as we pass through denser and emptier regions. Furthermore, the gravity from other nearby stars, even those passing at light-year distances, adds another layer of chaos to the calculation. Isolating the pure signal of the galactic tide from all this noise is like trying to hear a single, specific instrument in a symphony playing from another city. Yet, this galactic perspective is crucial. It means the Oort Cloud is not an isolated island. It is a dynamic interface, a place where the physics of our solar system meets the physics of the galaxy. The cloud's shape and stability are not determined by the Sun alone, but by the grand architecture of the Milky Way. Some models even suggest that these tides could be partly responsible for the timing of those great comet showers linked to mass extinctions. As the solar system bobs up and down through the galactic plane on its 225 million-year orbit, it might experience stronger tidal forces at certain points, potentially triggering heavier periods of comet bombardment. This connects the fate of life on Earth to the rhythm of the galaxy itself. Our story is written not just by our star, but by the silent, slow pull of 100 billion others, a reminder that we are part of a much larger, moving tapestry, and its gentle threads reach all the way to the frozen edge of everything we call home. The silent pull of the galaxy is a patient hand, but sometimes its work is not a gentle nudge, but a sudden, complete erasure. Our telescopes have witnessed a strange and final act in the cosmic drama, the case of the vanishing comets. These are long-period visitors, often from the Oort Cloud, that make their predicted approach toward the inner solar system, only to fade into nothingness before they ever develop a glorious tale. They simply cease to be. One of the most famous examples is Comet Linear, discovered in 2000. Astronomers watched as it broke apart into a cloud of tiny fragments before reaching its closest point to the Sun, a ghost before it could ever become a spectacle. This spontaneous disruption points to a fragile, icy structure, a loosely packed snowball held together by the faintest of forces. The heat of the Sun, even at a great distance, can seep into cracks and vaporize volatile ices deep within, building up pressure until the entire nucleus explodes from the inside out, turning a single comet into a diffuse, invisible cloud of dust. Another possibility is a silent, unseen collision. The Oort Cloud, while vast, is not completely empty. The space between comets is immense, but over millions of years, the odds of a collision, especially in denser inner regions, are not zero. A comet on its sunward journey could strike a rogue asteroid, another dormant comet, or even just a swarm of pebble-sized debris left over from the solar system's formation. At the relative speeds involved, such an impact would be catastrophic and quiet, shattering the nucleus into pieces too small to reflect light, a disappearance without a sound. Yet for some vanishings, even these explanations feel insufficient. This is where we must consider the exotic shadows that might populate the dark. Could a comet on its lonely path plunge through a dense, knot-like clump of dark matter? We know this mysterious substance gathers in halos, but some theories suggest it could also form finer, thread-like structures or micro-halos. If a comet passed through such an invisible knot, the sudden, intense gravitational pull from all sides could, in theory, rip it apart tidally, like a string of pearls stretched until it snaps. Even stranger is the prospect of a primordial black hole, one with the mass of a mountain but no larger than an atom. Such an object would be a perfect dark bullet. A direct hit would swallow the comet whole, leaving not even dust behind. A near miss, however, would be even more bizarre. The black hole's immense gravity would shred the comet into a stream of debris stretched into a line, a process called spaghettification, leaving behind a faint, linear trail of gas and dust that would dissipate before we could ever identify its cause. These vanishings are more than just celestial curiosities. They are critical data points, or rather, the absence of them. Each comet that disappears without a trace tells us that the environment of the outer solar system is not a pure vacuum. It is populated by unseen hazards and active processes. When we calculate the number of comets that should be arriving from the Oort Cloud based on its theorized population, and then compare it to the number we actually see, a discrepancy emerges. Some are missing. The vanishing acts could account for that gap, a silent solution to a quiet mystery. It means our inventory of the solar system is not just incomplete, it is actively being edited by forces we are only beginning to name. Every comet that winks out on approach is a final message, a testament to the fact that the journey from the deep freeze is perilous, and that some travelers never complete it, destroyed by enemies they never saw. The profound silence of the Oort Cloud may be more than just an absence of sound. It could be an engineered void. Astronomers mapping the cosmos listen not just for signals, but for the natural radio whispers of the universe itself. These are the emissions from hydrogen clouds, the faint crackle of distant quasars, and the gentle hiss of the cosmic microwave background. Yet, when they point their most sensitive radio telescopes toward specific regions of the outer solar system, aligned with the theorized plane of the Oort Cloud, they sometimes find something deeply unsettling: nothing. Certain bands of expected natural static are suspiciously muted, as if someone or something has turned down the volume on the universe. This radio quiet zone is a shadow in the ether. One potential explanation is chillingly natural. Perhaps the Oort Cloud is not just a collection of discrete comets, but is permeated by a vast, diffuse, and unknown cold medium. Think of an incredibly thin fog of molecular hydrogen ice or exotic carbon-based dust, too sparse to see with optical telescopes, but just dense enough to act like a cosmic sponge. As the faint radio waves from the galactic background travel through this fog on their way to Earth, specific frequencies could be absorbed, soaked up by the cold particles. We would see a blank spot on our radio maps, a hole in the cosmic noise, marking the silhouette of this invisible structure. It would be a new component of our solar system, a frigid atmosphere clinging to its outermost edges. The other explanation ventures into the realm of profound speculation, and it begins with a simple principle of stealth. Any advanced technology, especially one meant to observe without being observed, would minimize its emissions. Heat, light, and most critically, radio waves would be carefully contained. Now, imagine not just one hidden object, but a network of them, a distributed intelligence, as we discussed earlier, scattered throughout the cloud. If these constructs are designed with perfect stealth in mind, their collective effort to hide would create a zone of radio silence. Their shielding would not only prevent their own signals from leaking out, but could also inadvertently absorb the natural background radio waves passing through their vicinity. They would cast a radio shadow, a signature of absence. We would not detect their transmissions. We would detect where transmissions from the wider galaxy are being blocked. This shadow would not be a perfect dark circle. It would be patchy, shifting, and complex, mirroring the distribution of these hypothetical objects. Distinguishing between these two possibilities, a natural fog or an artificial veil, is the ultimate challenge. A natural absorbing medium would have a predictable, smooth effect across different radio frequencies, following the known absorption lines of specific molecules. An artificial stealth field, however, might look different. It could be too perfect, absorbing a wider than expected range of frequencies with an efficiency that defies natural chemistry. Or we might detect its edges, sharp boundaries in the radio silence that suggest a structured, technological origin rather than a random cloud. For now, this quiet zone remains a subtle anomaly in the data, a maybe, a perhaps. But its implications are deafening. If it is natural, we have discovered a new and mysterious component of our solar system's architecture. If it is not, then the silence we hear when we listen to the edge of our own home is not emptiness, but the sound of something listening back with the volume meticulously turned all the way down. The silence of a radio shadow could be the cloak of something far denser than a stealthy probe. A primordial black hole is a ghost from the very first second of time, and it might be our solar system's most ancient resident. Unlike the stellar black holes formed from collapsing stars, these relics are thought to have been forged in the unimaginable density of the Big Bang itself. A single one with the mass of Earth or Mars could be compressed into a sphere no larger than a grape. It is a knot of pure gravity, a tiny singularity drifting in the eternal night. If one were captured by the sun's gravity eons ago, its logical home would be the Oort Cloud, lost among trillions of other dark specks. There, it would be the ultimate dark object, emitting no light, reflecting nothing, and betraying its presence only by the subtle warping of space around it. Its influence would be a whisper, but a profound one. As it moved through the cloud on its own slow, cold orbit, its intense gravity would act as a cosmic plow. It would not just nudge comets, it would violently scatter them. We might detect a strange, fan-shaped pattern of disrupted comet orbits, all pointing back to a single, empty point in space, a gravitational scar with no visible source. Even more telling would be a lensing event. According to Einstein, a massive object bends the fabric of space-time, acting as a lens. If this primordial black hole passed directly in front of a distant star from our viewpoint, the star's light would not be blocked. Instead, it would be magnified and distorted, brightening in a specific, predictable pattern as the black hole's gravity focused the starlight like a cosmic magnifying glass. Our sky surveys that watch for such microlensing events, hunting for dark matter or exoplanets, might one day catch this signature from within our own solar system. The data would show a star briefly flaring, but the lensing object would have no associated heat, no reflected light, and a calculated mass far too dense to be any known planet or failed star. It would be a mathematical phantom with the weight of a world. The implications of finding such an object are staggering. It would be a direct sample of the universe's birth, a fossil from the moment of creation sitting in our celestial attic. It could solve multiple mysteries at once, perhaps accounting for the strange clustering of distant objects we attribute to Planet 9, or even acting as the unseen engine for that cosmic ray hotspot. This hypothesis transforms the Oort Cloud from a simple storage locker into a cosmic curio cabinet, holding not just ice and rock, but a pinprick of infinite density, a silent reminder that the most extreme phenomena in the universe can hide in the quietest corners, waiting for a passing star's light to reveal their impossible weight. A primordial black hole is a ghost, but the cloud it haunts might have walls. Our 24th phenomenon confronts a fundamental assumption about that distant shell, the idea that it is a uniform, fading haze of icy objects. Theoretical models now whisper a different story, one of sudden edges and abrupt boundaries, a place where the density of frozen worlds does not gently taper off, but instead hits a cliff. This is the concept of the Oort Cloud Wall, a density discontinuity that would make our solar system's frontier not a soft border, but a structured, almost architectural feature. Picture the classic model as a vast, diffuse sphere, with comets scattered ever more sparsely the farther you go, like smoke dissipating in still air. The wall hypothesis suggests that at a certain distance, that smoke simply stops. On one side, a teeming reservoir of ancient ice, on the other, a comparative void. What force could possibly build a fence at the edge of nothing? One of the most compelling architects is a stellar intruder from the deep past. In the sun's youth, when it was still nestled in its birth cluster alongside hundreds of sibling stars, close encounters would have been common. A passing star venturing too near would have done more than just scatter comets. Its gravity would have acted as a cosmic shear, a pair of scissors snipping through the outer reaches of our protoplanetary disk. It could have cleanly stripped away the most distant material, carving a sharp outer edge to the cloud before sailing off into the galaxy. The result would be a fossilized boundary, a wall marking the maximum reach of that ancient stellar tide. We would see a sudden drop in the number of long-period comets originating from beyond a specific, calculable distance. Another builder could be a resident giant, not a passing star, but a permanent hidden one. The gravitational influence of a massive object like Planet 9, if its orbit is confined to a specific zone within the cloud, could shepherd material. Its repeated passes could clear a lane, hoarding comets within its sphere of influence and evacuating the space just beyond its reach, creating a dense inner ring with a relatively empty region outside it. This would not be a wall at the cloud's absolute edge, but an internal barrier, a ringed structure within the vast shell, invisible to us but sculpted by a hidden master. Perhaps the most profound possibility is that the wall is not a feature carved later, but a relic of the very beginning. The solar system did not form in isolation, but from a collapsing fragment of a giant molecular cloud. This fragment had its own boundaries, its own density gradients. As the sun ignited and the planets coalesced, the outermost icy material that failed to condense into planets might have simply retained the imprint of that original cloud fragment's edge. The Oort Cloud, in this view, is not a scattered diaspora, but a preserved cast, a perfect fossil of the nebular bubble that birthed us. Its outer wall would be the mold line, the place where our particular piece of the cosmic nursery ended and the void of interstellar space began. Detecting such a wall is a challenge of statistics and patience. It requires mapping the precise origins of thousands of long-period comets, tracing their paths back not just to the Oort Cloud in general, but to specific distances within it. If we find a consistent cutoff, a distance beyond which virtually no comets seem to originate, we will have found our wall. That discovery would force a dramatic rewrite of our solar system's biography. It would tell us the precise size of our original birth cloud, or reveal the mass and passage of a star that brushed us 4 billion years ago, or confirm the existence and orbital domain of a hidden giant. The wall would be more than a curiosity. It would be a historical document, a line drawn in the frozen dark that says, "Here and no farther, this is where our story is contained." 70,000 years ago, as our ancestors gazed at the same night sky we know today, a faint red ember drifted silently through the solar system's darkest attic. We know this now because astronomers have traced its path, identifying a dim binary system known as Skol's star. This visitor, a small red dwarf star with a brown dwarf companion, did not just pass nearby. It plunged directly through the outer Oort Cloud, coming closer to our sun than any other known star. Its passage was a whisper in the dark, a gravitational hand brushing through a field of sleeping comets. For the creatures on Earth, the event was invisible, but in the deep freeze, it may have left a permanent signature, a ripple still echoing through time. The lasting impact of such a flyby is not in the immediate chaos it creates, but in the subtle, long-term rearrangement it engineers. As Skol's star moved through that sparse sea of ice, its gravity acted like a celestial comb. Some comets, those on the star's approaching side, would have been pulled along, given a slight boost of energy that could have flung them out of the solar system entirely, lost to the interstellar void. Others on the trailing side would have experienced a gravitational tug backwards, a braking force that stole a tiny amount of their orbital energy. This is where the real mystery takes root. For these trailing comets, that stolen energy is critical. Their already vast, loosely bound orbits became a little bit smaller, a little bit tighter. They were not ejected, but instead shepherded into new trajectories that curve more sharply sunward. We may be living in the aftermath of this stellar brushing, yet we see no immediate storm. The comets affected by Skol's star are not on fast, direct routes. Their new orbits, while altered, are still immensely long, measured in hundreds of thousands or even millions of years. This means the full consequence of that flyby is not a sudden downpour, but a slow, deliberate migration. A distinct population of comets bearing the unique kinematic signature of that encounter could now be on their way inward. They are the delayed echo of a past event, a wave of icy travelers set in motion when humanity was just beginning to tell stories around campfires. Our telescopes have not yet seen them coming because their journey is only a fraction complete. They are the ghosts of a past encounter still falling toward the light. This single event forces a dramatic shift in perspective. If a star passed this close so recently, in the mere blink of a galactic eye, then such close encounters cannot be rare cosmic flukes. They must be a regular feature of our solar system's life. Our sun, like all stars, is moving through a dynamic neighborhood. We are not sailing through an empty ocean, but through a crowded harbor. Current models suggest a star passes within the Oort Cloud's domain roughly every 100,000 years. Each one is a sculptor, each passage a gentle or not so gentle remodeling of our outermost borders. Over the eons, our Oort cloud has not been a static, pristine relic. It has been stirred, poked, and reshaped by a parade of silent, drifting neighbors. This realization transforms the Oort cloud from a distant museum into a dynamic construction site, its shape and contents constantly being revised by galactic traffic. The comets we see today, the long-period visitors that grace our skies, are not simply primordial leftovers. They are the products of a history of stellar interactions, each bearing subtle clues about the stars that have passed by. Finding and studying comets with strange, hyperbolic orbits that cannot be explained by planets alone might let us backtrack, identifying the direction and timing of ancient flybys we never witnessed. The cloud becomes a guest book signed by passing stars, with each gravitational signature left in the altered paths of a billion icy worlds. Scholz's star has already faded into the distance, now over 20 light-years away. But its legacy may still be unfolding in the frozen dark. It serves as a potent reminder that our solar system is not an island. We are connected to the galaxy by these invisible threads of gravity, touched by the passage of other suns. The next stellar visitor could already be on its way, another red dwarf or a cold brown dwarf, destined to weave its own pattern into the cloud. When it arrives, it will once again rearrange the furniture in our farthest attic, setting in motion a new wave of comets whose journey will conclude long after our civilization has become history itself. The universe is in constant, quiet conversation, and the Oort cloud is where we can overhear its whispers. The story of Scholz's star is a single thread in a tapestry woven from 25 profound mysteries. From the ghostly tug of a missing planet to the silent watch of ancient probes, from the frozen echoes of stellar flybys to the potential warmth of hidden oceans, each phenomenon we have explored paints the Oort cloud not as an empty void, but as a vibrant frontier. It is a place where the lines between established science and thrilling speculation beautifully blur, where every unanswered question pushes the very boundaries of what we think we know about our cosmic home. This distant shell is more than a collection of ancient ice, it is a challenge. It dares us to look beyond the familiar planets and acknowledge that the solar system does not end where our telescope's clarity fades. It extends into a realm of whispers and shadows, of mathematical ghosts and potential artifacts, a realm that holds the keys to our past and perhaps the blueprint for our future understanding of the universe. The greatest discovery is the realization of how much we have left to discover. So what do you believe is out there? Was your mind captured by the dark matter donut, the eerie precision of the wow signal, or the patient logic of a Bracewell probe network? Share your favorite theory in the comments below. This conversation is just beginning. If you are hungry for more journeys into the unknown, make sure to subscribe and ring the bell for our next exploration into the deep space mysteries that surround us. Never stop looking up and never stop wondering, for in the deepest, coldest dark at the edge of everything we know, the greatest stories are still waiting to be told.